All right, hello and welcome to the wolfSSL live webinar, migrating from OpenSSL to wolfSSL with our engineer Jacob. My name is Marcos and I'll be moderating the webinar today. All attendees will be in listen-only mode. If you have questions, please use the Q&A button at the bottom of your screen. We'll be answering questions following the presentation. The webinar will also be recorded and uploaded to our YouTube channel shortly after. I invite you to follow us on Twitter at wolfSSL, as well as our other socials. Also, feel free to email us at facts@wolfSSL if you have any additional questions, or if you want a copy of the slides after the presentation. And I'm going to give a quick company overview before we start the presentation. wolfSSL was founded in 2004 by Todd Oska and Larry Stefanich when they realized there wasn't an open source, well-licensed embedded SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and modern API, and offered commercial-style developer support. wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of almost 50 dedicated employees in 2022, most of which are engineers. This progress is of course supported by a strong partner network that we're proud of, which includes DDCI, STMicro, and RTI, for example. Since the beginning, our engineering team has developed several embedded security products, including wolfcrypt with DO-178 support, FIPS certification, and FIPS ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, bootloader known as wolfboot, as well as Java wrappers and JSSE support for curl. All of these offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. And that's all for me. I'm going to hand it over to Jacob now for the presentation. Thank you.
Thank you, Marcos. As mentioned, today I'll be covering a bit about the wolfSSL compatibility layer. I'm going over the four main topics of what is the wolfSSL compatibility layer, building wolfSSL with the compatibility layer enabled, a simple example application demonstrating its use, and the examples of major projects that the feature has been used in. And then on the last slide, I'll go over a little bit about the feature of the compatibility layer, and at the end we'll open it up for any questions. So there's a lot of products that wolfSSL has. One of those is the wolfSSL compatibility layer. This provides a means for making calls to wolfSSL native implementations of functions that behave similar to the OpenSSL APIs. With the use of macros, it maps a subset of the OpenSSL APIs down to wolfSSL native APIs. And the compatibility layer is constantly getting expanded upon as new projects get completed, and there are currently more than 800 of the most commonly used OpenSSL APIs supported. This maps, like I mentioned, a subset of the most common APIs. It's not necessarily just TLS APIs. We have quite a few EVP APIs mapped down to native wolfSSL implementations. We also have a lot of bio APIs for their basic input-output mapped down to native wolfSSL APIs. And these mappings that we have in our header files is all isolated to the wolfSSL OpenSSL directory. It's meant to be a drop-in replacement if you already have OpenSSL working in your application. With that drop-in replacement, you don't need to necessarily change the header files because we have the same name of the header files containing the mappings. I'll go into that in a little bit more detail later. So covering a bit more about the crypto API supported, there's support for EVP init, update, and final function calls. In addition to the init, update, and final functions, there's signing and verifying EVP API available. These EVP functions are abstracted functions that OpenSSL uses for many different underlying algorithms, such as performing an RSA signature operation or with doing AES encryption. There's additionally support for direct calls to hashing algorithms, like the SHA and SHA-256 as examples, along with support for direct calls with AES encrypt and encrypt. And what I mean by those direct calls is not just the EVP abstraction layer. We have some of the lower level crypto API also mapped to wolfSSL's native implementations. And we have a support for peak key. Peak key is commonly used for the public key operations. We have a wolfSSL implementation of that structure that can be used for ECC and RSA. There's also a little bit of a DSA addition to that. And then we have the X509 API mapping in addition to those. And there's many more mappings that we have than what's just listed here, but these are the common use cases for the non-TLS, is with the X509 wrappings that we have and the EVP. So the problem that the compatibility layer solves with having all of these APIs and structures mapped is to allow for easily migrating from OpenSSL to wolfSSL. This is with having an unaltered application that was previously linked to OpenSSL and migrating it to wolfSSL by only updating the link and include paths. And here's a brief snapshot of the main header for the wolfSSL compatibility layer. It shows places where the names of OpenSSL structures get mapped to wolfSSL implementations. It also shows a couple of the main TLS API mappings. And the bulk of the code mapping APIs will be located in the SSL.h file. So that's wolfSSL, OpenSSL, SSL.h. That has the bulk of our type def remapping and our defines remapping the functions. So you can include the same OpenSSL, SSL.h in the application, not altering that include path. And then these macros here would remap the functions in your application to then be calling the native wolfSSL versions of them. And those are wolfSSL implementations of those functions that have been written from scratch by wolfSSL engineers to behave in a similar way. Before getting into the example applications and how to build wolfSSL for use with the compatibility layer, I'd like to cover why someone would want to turn on the compatibility layer feature and why they may want to migrate from OpenSSL to wolfSSL. There are many reasons for wanting to make this migration. I've listed some of them on this slide. One reason is that there is a lot of hardware acceleration ports that wolfSSL offers. These can be the same hardware accelerations that you might see in OpenSSL, the well-known ARM assembly and Intel AES&I, for example. But wolfSSL also has a lot of embedded hardware accelerations. So if you're working on something like an XP device, we have a lot of hardware acceleration support with NXP. Some of the STM32s, for example, we have a hardware acceleration support there as well. Another point of interest to many is the addition of progressive algorithms, and such as the early adoption of TLS 1.3. We also have a reduced footprint size. A couple of slides later, I'll do a comparison between footprint size with the same application linked to OpenSSL and then just switching the link over to wolfSSL. It's pretty dramatic reduction of footprint size, which lends itself well to both embedded devices and scales well to something such as like a large server farm. With the reduced footprint size, you can do more TLS connections with the same amount of resources. wolfSSL is supported by the wolfSSL engineers who work with and develop the code. So if you have a support case or some issue that you want to get help on, you can ask directly to the wolfSSL engineers who wrote the code. And there's a clear licensing model. So it's dual license, GPL, V2, and then commercial license. We also have the potential to use wolfSSL with FIPS. One of our slides later goes into a little bit more detail about the FIPS situation with OpenSSL, which is not great at the moment. But we have current support with FIPS, and we're also going through the FIPS 140-3. Okay, so OpenSSL FIPS, it dropped to historical list in September of 2020 due to the implementation guidance G18. And it seems like FIPS hasn't been such a priority of OpenSSL, which we find a lot of people working with government projects, they need the FIPS certification to be able to fulfill the requirements for government projects. With the wolfSSL compatibility layer, it is easy to plug wolfSSL into a project that will be affected by this lapse of OpenSSL FIPS coverage. Plugging in wolfSSL will keep the project up to the standards and possible requirements from the projects. The wolfSSL, the FIPS certified code with wolfSSL is used in many existing projects, and a full list of our supported OEMs can be found on the NIST site or up on the wolfSSL website. There are multiple Linux projects listed there that have been done. The list even includes Android and FreeRTOS. So OpenSSL's FIPS status with OpenSSL 3.0 is currently in the review process. So they do have some code that's going through the FIPS certification process, but it hasn't received its certification yet. And so we have this FIPS ready build bundle that we have available that contains the same code that would be used for a FIPS certification. So you can download that code. It's under a GPL v3 bundle. So you can download that and experiment and get your project ready for FIPS certification using the FIPS ready bundle before going through the FIPS certification process. So that covers the basics for what the wolfSSL compatibility layer is and its value when used with the project. Next is going through the steps of turning on the feature when building the wolfSSL library. So to build with the compatibility layer enabled, when using auto tools, the flag -- enable OpenSSL extra is used. In addition to the OpenSSL extra flag, there is also an OpenSSL all. OpenSSL all enables a superset of implemented functions by including some of the API implemented when expanding for use with new open source projects. If building in an IDE or cases where auto tools is not being used, then the macro OpenSSL_extra can be defined. This macro can either be passed as a preprocessor flag, or better yet, it can be set in a user_settings.h file. When linking against the wolfSSL library and having built using auto tools, the file wolfSSL options.h should be included first before any other headers that are used for wolfSSL. This is to make sure that all of the defines that were set when building the library are also carried in to the includes in the application and set the application so that it's up to mesh with how the library was built. So all header files needed for migrating an application over to wolfSSL are located in the directory wolfSSL OpenSSL. An example of that is the SSL header file that we went through earlier that's located in wolfSSL OpenSSL SSL.h. And this is to make it so that you can change the include path rather than the includes in the application itself, and be able to then have the application still find the same header files without having to adjust the includes in the application itself. Okay, with the internal behavior of wolfSSL being different than OpenSSL, there are some cases where only stub functions were needed in projects. These are functions that allowed for compiling the code, but do not actually do anything when called. I think a great example of that might be with like Blowfish. wolfSSL does not have an implementation for Blowfish, but some applications are making calls to the OpenSSL Blowfish. Most cases, these aren't used at runtime. At least in most of the cases that I've encountered, it's not used at runtime. So we have a stub function that would handle the passing the compile time, but it would just return an error if someone was to actually try and access Blowfish at runtime. It's also the case that when migrating some projects over to wolfSSL, the features were not needed. So the functions were not finished at that time. It can be useful to tell whether your application is calling a stub function or not. So to help with that, either the debug feature can be turned on, and this is what the --enable -debug, or the macro no_wolfSSL_stub can be defined. Turning on debugging prints out a warning message each time a stub function is called, and defining the no_wolfSSL_stub macro will throw compile time errors if the application is attempting to use any stub functions. And that's a macro that we use wrapping around all of our stub function implementations that just compiles them out if it is defined. Yeah, wolfSSL is a very modular library in how it can be built and configured. With this being the case, additional features such as the key generation would also need to be turned on at compile time if key generation support is wanted. So OpenSSL Extra enables the use of our compatibility layer, but then to turn on things such as like the key generation, or say if you wanted OCSP, for example, or wolfSSL so modular to be able to fit in reduced resource or resource constrained environments, we have the additional enable keygen or enable OCSP, for example, that would need to be used at compile time. So there's a couple of alternatives that we offer to the compatibility layer. These are relatively new developments. One alternative to use is the Wolf engine. What the Wolf engine does is OpenSSL has this framework where you can plug in engines as a crypto suppliers. We have an implementation to be able to plug in using that framework that OpenSSL has. It's been tested with wolfSSL FIPS using OpenSSL 1.02 and 1.1.1. I believe it's been tested with a couple of more versions of OpenSSL at this time. It's one of our popular uses for the FIPS certification labs that OpenSSL has. It's a quick way to add in FIPS certified crypto underneath the OpenSSL TLS and EVP layers. We also have automated unit tests and continuous integration tests with the Wolf engine that we have up on our GitHub. Release 1.0.0 just came out last week, and it's available for download. It's a GPL v3 or commercial. And like I mentioned, that we have the public GitHub repo up, wolfSSL-wolf engine, if you want to see the commit history or the leading edge of the development. In addition to the Wolf engine, we have a Wolf provider. Wolf provider frameworks are for the OpenSSL 3.0.0 and later. So OpenSSL changed it from being engines to providers, and we made an implementation for a provider in case someone needs a FIPS certified crypto immediately, it's an easy swap out to be able to plug in the provider to then fulfill FIPS requirements. And there's also a public GitHub repo, GPL v3 or commercial. It's up on the wolfSSL /wolf provider. That covers the basics for how to build the wolfSSL library in preparation for the Great Migration. The next items are covering how to use the library once built and example cases of projects that the feature has been used with. When migrating an application from OpenSSL to wolfSSL, one of the things that needs to be resolved is including the right header files. OpenSSL headers should no longer be used, and the header files located in wolfSSL should be used instead. This is typically achieved in one of two ways. The first with being changing the preprocessor include path to point to the wolfSSL directory with the OpenSSL compatibility header files. The second being by changing the application code to have wolfSSL prepended to the includes. In most projects, we offer the first option because it does not require any code changes to the application itself and is done by simply adding a preprocessor flag when compiling. The next thing that needs to be updated when migrating a project over is the library that it is linking to. When an application is linked against OpenSSL, it uses the -L SSL and -L crypto. This should be changed to be -L wolfSSL so that the application is now linking with the wolfSSL library instead of OpenSSL. After updating the link and the include path, the migration is complete. And then the application can use the API as it would before having migrated over. It just calls down then to the native wolfSSL API. So here are two examples of altering the include path and library link to. The source file, the great _ migration, is a simple TLS server written for this demonstration that uses the OpenSSL APIs. The first example command line executed has the application using OpenSSL headers and linking to the OpenSSL library. The second command line executed on this slide shows updating the include path to point to the directory where wolfSSL headers are. In addition to adding the include path, I also used the -include flag, which tells the compiler to include wolfSSL options.h as the first include file when compiling any source code. As you remember earlier, when using AutoTools, this options.h has to be included as the first include path to make sure the application is using the same setup as how the library is built. And that's an easy way to do it at the command line when it's compiling rather than adding it into the application. And finally, to have the application linked to the wolfSSL library created, the links to SSL and crypto were changed to be -L wolfSSL. From executing each of these commands, open.out executable was produced when linked to the OpenSSL library, and wolf.out executable was provided when linked to wolfSSL. This slide shows a small code snippet of the example TLS server used. It shows the bulk of the TLS code after a certificate has already been loaded and the client has initiated the TCP connection. And the code only OpenSSL API was used, which when using the wolfSSL compatibility layer, it gets mapped down to wolfSSL native API. And this slide highlights the difference in heap used with different builds for each of the libraries. To collect the heap usage, I built the application on Ubuntu 18.04 and used Valgrind's massive tool for the generation of the graphs. In both cases, the cipher suite used was the same as the ECDHE RSA AES 256 GCM with SHA 384. And the same client was used to connect to both servers. With OpenSSL, let's see, version 1.1, the peak heap used during the connection was 202.6 kilobytes. In contrast, when linked against wolfSSL version 5.2.0 with just /configure enable OpenSSL extra, it was 38.1 kilobytes. And each of these examples was the same server application. The only thing that was changed between the two executables was which library it was linking to, whether it was linking to the OpenSSL 1.1.1 or whether it was linking to the wolfSSL's compatibility layer. So it's a dramatic difference, less than a quarter of the heap usage. Yeah, and I did a second run with OpenSSL 3.0.0, and it was even more dramatic difference. So it was 841.4 kilobytes for just a single connection with OpenSSL 3.0.0. A lot of that I would suspect is due to like the provider setup that they have in OpenSSL 3.0. So not necessarily every single connection is going to be that 840. I think if you did successive connections after the first provider setup, it was around 100 kilobytes, if I remember correctly. So it's still significantly larger than the 38.1 kilobytes that it takes with wolfSSL 5.2.0. And then that was just a -- enable OpenSSL extra in the previous one with wolfSSL. We have additional optimizations both for speed and for memory usage. So you may be curious in that previous slide whether or not our performance, how our performance compares to OpenSSL with smaller heap usage. This is showing one of our more performant builds. So we have the SP math all small version of it, and then an enable SP small. SP is single precision. It's optimized for the commonly used public key operations in TLS Handshake. So RSA 2048, 3072, and ECC 256-bit. And it actually used less memory, so it only consumed 27.1 kilobytes of heap. The code size would be a little bit larger with this one, but not significantly larger. That covers an example of using the compatibility layer and the resource use reductions that you can see. The final item before going into the future of the compatibility layer covers some examples of major projects that it's been used in, and a couple of steps of determining how all APIs needed for migration of your project are available. So this is a list of some of the major projects that the compatibility layer has been used in. For many of the major open source projects that we port to with the compatibility layer, there is an associated enable option. This is just to guarantee that all features used by the open source project are enabled when wolfSSL is compiled. An example of this would be to use the enable nginx or enable HA proxy flag. The full change is done with nginx. Apache can be found on our wolfSSL GitHub repository. We have a separate repository for hosting the nginx, and then we have the what we call OSP repository, which a lot of our open source projects that we've ported to. And this enable nginx or enable HA proxy, it turns on things such as like a keygen if it is used heavily in the project, or for example, a CSP if it's used in the project. It makes it easier to just configure wolfSSL for use with the port that was done. Okay, with the compatibility layer being a subset of all possible OpenSSL API, there is a chance that some API used in your application may not yet be implemented. Again, we have over 800 of the API, and that's constantly expanding as we do more projects that are switching away from OpenSSL and coming to wolfSSL. But it's still not a one-to-one. We don't have 100% of the OpenSSL APIs. We just have the most commonly used ones. Most new projects that I'm seeing anymore, it boils down to a couple missing API. Since we have so many of the commonly used API. But the easiest way to tell if there is some missing gaps in the implemented API is to compile the application and just link it against wolfSSL. Again, we have that GPL version of it up on our GitHub that can be downloaded and tested with. This will list out compile time errors for all unimplemented functions. If it is found that any API are missing, we do accept feature requests, or we can offer consulting for expanding the compatibility layer as needed for projects. And a lot of the projects that we encounter where we're expanding it, it's like I'd mentioned, a couple of API. Yeah, and if too many API are missing, wolfcrypt can be used as an engine. That was something that I brought up earlier, our wolf engine and our wolf provider. So some people that we've worked with, when they just have, when there's 50 or more API, because it's using so many different open source projects, or a lot of different applications are being ported at once. They may opt to use the wolf engine to start with, or the wolf provider to start with, just to have the crypto operations being secured by our wolfcrypt library. Yeah, and for the future of our compatibility layer, we implement additional compatibility API as needed. So each port we do, as I mentioned earlier, it seems has less and less API implementations required, just because we've been expanding the compatibility layer to cover so many of the commonly used API. Some of the things that we have on our radar is additional open source projects ported to use wolfSSL. That's something that we're always looking for, is which next open source project we should port over. And then we have a revamp of what we call wolfCLU. The CLU stands for command line utility. It's a replacement for the OpenSSL command line utility. We implemented a lot of different commands and features just to the end of last year. That's on our it's on a public repository in wolfSSL/wolfCLU on our GitHub. It can also be seen in our alternative downloads up on our download page. And it's getting closer and closer to being what I would consider close to the feature complete. Right now it has all of the implementations for certificate generation, signing certificates, key generation, PKCS12 parsing. So it has a lot of the major features that the command line that you would expect from something like the OpenSSL command line utility. So that gives a summary of what the wolfSSL compatibility layer is, some of why it would be used, and example cases for switching from OpenSSL over to wolfSSL. And I think at this time we'll go ahead and open it up for if there's any questions.
Yeah, we got a couple questions. So I'll start with this one. This is a two-part question. Which features conflict with OpenSSL extras, and can the same library be used for both for direct wolfSSL and OpenSSL?
So we have this coexist flag to make it so that you can call the wolfSSL native API and then still be calling the OpenSSL API. The compatibility layer cannot be used at the same time as an OpenSSL library. So it would have to be either be you're using the native API and then the OpenSSL API, or you have to replace and remove OpenSSL and then use the compatibility layer.
Okay. Next question. Your example C programs are not MISRA compliant. Is the wolfSSL code itself MISRA compliant?
So we took a small subset of the crypto through some MISRA C enhancements and MISRA C compliance. The TLS level we have not. If I remember correctly, it was like the RSA and AES .c that we did some MISRA C work on. But yeah, the whole of wolfSSL is not fully MISRA compliant, no.
What is commonly used for certificate management, i.e. for certificate revocation?
So we have the CRL implementation for certificate revocation list. I mean, there's also the OCSP implementation that we have, OCSP stapling. Either one of those could be used for certificate revocation. To build wolfSSL with them, that's the enable-CRL and then enable-OCSP for the OCSP one. And then we have a couple of like unit tests and examples that can be seen of using that.
Another question. We use boost/beast. Can we build boost so it would use wolfSSL in a FIPS compliant mode?
Sorry, can you repeat that question?
Yeah. We use boost/beast. Can we build boost so it would use wolfSSL in a FIPS compliant mode?
Yeah, if I remember correctly, we did do a port of boost over to wolfSSL, and you would be able, anything that wolfSSL can be used in, you can use the FIPS version of wolfSSL. As far as FIPS compliant, you'd have to make sure that it's using the right algorithms and the right RSA key sizes. That is also part of the compliance. But yeah, we could do that. If you shoot us an email at facts@wolfSSL.com, I can follow up with a call and take you through the steps of it.
Another question. For use in real-time, high reliability end devices, is it possible to replace heap usage with reusable static memory blocks in wolfSSL?
Yeah, so we have a feature called the static memory, and that can be enabled with --enable-static memory. It handles a big section of the heap. You might run into an edge case where there's one malloc or another that needs a touch-up to be redirected to the static memory feature. But what that does is that you can create just a static buffer and then point all mallocs to that static buffer. So it instead of allocating heap, it'll use a section of that static buffer.
Another question. Can the same wolfSSL library be used for both apps using wolfSSL directly and open source apps using extras?
Yeah. So you can use the wolfSSL native APIs in addition to the OpenSSL extra APIs. The only time you run into an issue is when trying to link to the two libraries at the same time, OpenSSL and wolfSSL. But yeah, you can still call the native APIs with the OpenSSL extra enabled.
That was the last question. We just wait a couple seconds in case someone's typing something out.
Sure. Yeah, great question so far.
Okay, we got another question. So it seems that wolfSSL compatibility layer and OpenSSL Wolf engine serve the same purposes. What are the different use cases for both?
Sure. It's a good question. The difference between the compatibility layer and the engine is with the engine, you still have the OpenSSL TLS code, and you still have the OpenSSL EVP code. So in that case, you're basically just plugging in the Wolf crypt, so it's just the crypto operations, and you would still see the code and bloat and all of the larger heap use that OpenSSL has with their TLS and EVP implementations. With the compatibility layer, what's happening is the OpenSSL library is actually removed from the equation, so you no longer are linking to OpenSSL. You have the wolfSSL TLS implementation and all of the wolfSSL wolf crypt code. I hope that clears it a little bit.
That might have been the okay, yeah. That might have been the last question. Oh wait, no. One more question. I think he's just typing it out. Just wait a second. This question is this going to be supported in the meta wolfSSL Yocto layer?
Yeah, so I can't remember what the default build is in the meta layer, but I think it's just default configure. You'd have to add in the enable OpenSSL extra or enable OpenSSL extra. And if I remember right with Yocto, that can be done with in like the BB layers conf file or the local.conf file. I think that would be a quick add-on to be able to add that enable option when it's being built with Yocto. But we do have Yocto meta layers. That brings up a good point. We have those Yocto meta layers up on our GitHub repository. So if you look at wolfSSL / meta-wolfSSL, that's all of the meta layers that we have.
I think that might have been our last question. So just to remind everyone again, if you have any additional questions, you can email fax@wolfssl.com, or if you want a copy of the slides, you can also send an email there for that. But yeah, it seems like we don't have any more questions, so we can.
All right, yeah, thanks everyone for attending, and thank you, Marcos.
Yep, thank you everyone for your questions. Thank you, Jacob, for the presentation.